The air over Radar Picket Station 14 hung thick and humid, heavy with the expectation of violence. It was late October 1944, off the Philippines, and the crew of the USS Stanley, a Fletcher-class destroyer, was not waiting for an attack. They were waiting for the inevitable. Up high on the tripod mast, the Mark 12 and Mark 22 radar antennas spun, painting the unforgiving reality of the night sky onto the screens below. A report sliced through the low hum of the emergency diesel generators. Contact, bearing 030, range 12,000, closing fast. That backup power source was critical, meaning the difference between life and death if the main feed was cut. The blip was not maneuvering like a conventional bomber. It was descending at an angle that defied sane aerodynamics, a single-minded streak of malice. General quarters sounded, the alarm klaxon screaming its mechanical warning across the deck as men sprinted to their stations. On the centerline, the 40mm Bofors guns, deployed in their distinctive quadruple mounts, swung violently toward the threat. The gunner on the Mark 51 director, a simple, one-man unit with a joystick control, locked on immediately. This desperate, pragmatic wartime invention lacked the complexity of the larger Mark 37 system, but under fire, its simplicity was its strength. He had mere seconds to react. The 5-inch/38 guns opened first, their thunderous report momentarily deafening the entire forward section of the ship. The variable time proximity fuses, the technological shot in the arm that had partially concealed the inherent weaknesses of the older systems, were doing their work. Shells detonated not on contact, but when the radar signal bouncing off the aircraft indicated it was within the lethal radius of the blast. The sky ahead became dotted with furious, expanding spheres of shrapnel. The first kamikaze aircraft, a converted Zeke fighter carrying a 500-kilogram bomb, plunged through the barrage. The gunners could hear the high-pitched whine of its engine over the roar of their own fire. The Mark 51 operator, his face slick with sweat, held the joystick steady, compensating for the destroyer's violent roll as she turned hard to present a smaller profile. The order, hold fire, was useless. The automatic weapons took over in a desperate, last-ditch attempt. The Bofors barked, spewing a torrent of high-explosive tracer rounds, each one a glowing, angry bee aimed at the descending speck. The 20mm Orlicons chattered frantically, their smaller rounds acting as a vital warning system for the machinery space crews to evacuate. The sheer volume of fire created a visible, blinding wall of steel and flame, the incoming aircraft already riddled. Clipped the destroyer's flagstaff with its wing, the sound a horrifying, tearing shriek of stressed metal. It missed the main structure, splashing violently 100 yards off the starboard beam. The concussion slammed against the hull, knocking the gunners off balance and filling the air with the acrid smell of cordite and burning oil. The Stanley had survived this time. But the experience was a terrifying confirmation of how dangerously close the navies of the world had come to fighting the war with obsolete tools. But to understand this desperate high-speed defense, we must look back to the economic ruins of the 1930s. The Great Depression, beginning in 1929, acted as a global tourniquet on military innovation. In Britain, the damage was compounded by the disastrous 10-year rule, a policy that deferred military spending based on the optimistic assumption of no major war for a decade. This led to a significant deferral of modernization and the procurement of necessary anti-aircraft systems and expendables. British ship designs, already tightly engineered, struggled to accept much additional light armament, a stark contrast to the massive increase in automatic weapons the US Navy would manage later. Across the Atlantic, the US Navy found itself similarly constrained, not just by budget, but by the Washington Naval Treaty System. Tonnage limits forced naval architects to consolidate capability, leading to the doctrine of the dual-purpose gun. This doctrine culminated in the development of the 5-inch/38 caliber weapon. It was an engineering marvel, designed to fire a 54-pound shell at 15 rounds per minute, fast enough to track an aircraft, yet powerful enough for surface combat. Though the Bureau of Ordnance had considered a heavier 5.4-inch gun, the resulting 75-pound shell was simply too heavy for men to handload at a high rate, especially at high elevations. The physical limits of the sailor, the need for ammunition to be light enough to be handled quickly in a lively ship, dictated the caliber of the primary wartime defense. Yet even as the new weapon was being installed on the Farragut-class destroyers and the Yorktown-class carriers, The technological threat was already outpacing the defense. The moment of bitter clarity arrived in the late 1930s. Up until then, gunnery exercises had been largely theoretical, firing at towed sleeves or making calculations based on assumed target movements. But by 1938 and 1939, the Navy introduced drone targets for simulated attacks. The results were horrifying. Cruiser captains watched in dismay as the lumbering 5-inch/25 caliber guns, common on older ships, struggled to track the fast, maneuvering radio-controlled aircraft. The drones often flew so close to the ships that tracking and range-keeping were almost impossible. The core problem was not just the gun, but the fire control system itself. The analog computers, which had to measure the target's position, calculate its course and speed, and then predict where the shell would arrive, were hopelessly slow. Time and again, exercises showed that even the best anti-aircraft batteries struggled to hit maneuvering targets. The brutal reality was grimly summarized. The aircraft would always be about 20 seconds ahead of the rangekeeper solution. The fleet's unhappiness grew when they observed the hits. Even when the 5-inch shells burst near a drone, the target often seemed to continue, emerging unscathed or returning to base with numerous holes in them. The conclusion was stark: individual shells were not lethal enough, and the systems lacked the speed and precision to deliver them reliably. The British, relying on the octuple 2-pounder pom-pom, fared little better, discovering that the director-controlled low-velocity gun was often less effective than a locally controlled gun using high-velocity ammunition. Admiral H.R. Stark, then Chief of Naval Operations, was jolted by the British experience off Norway in 1940, which proved the air threat was far beyond anything the Navy was prepared to resist. He tasked Admiral Ernest J. King with finding immediate solutions. King's urgent assessment prioritized the installation of the quadruple 1.1-inch machine cannon on every capital ship. This weapon was flawed and difficult to maintain, but it represented the only available stopgap. The U.S. Navy, the pioneer of dive bombing as an offensive tactic, suddenly found itself rushing to defend against the very tactic it had perfected. They were forced to fight a global war with systems that, just months before, had failed miserably against an empty, radio-controlled drone. The desperate race for technological survival had begun in earnest. The fundamental problem of naval anti-aircraft defense was never about metallurgy or explosive power, it was about geometry and time. A capital ship was a constantly moving platform, subject to the unpredictable, nauseating forces of the sea. Roll, pitch, and yaw continually entangled the two key angles, elevation and bearing. To hit an aircraft, the gunner first had to cancel out this inherent trunnion tilt. Then he had to simultaneously solve a dynamic three-dimensional problem. He had to measure the target's present position, calculate its angular rate of change, and predict where it would be a full 20 seconds in the future when the shell finally arrived. Since directly measuring these complex rates in real time was impossible for early mechanical systems, designers turned instead to synthetic fire control. These analog computers were mechanical models requiring operators to manually feed in the estimated target course and speed. If the operator guessed wrong, the entire firing solution collapsed instantly. This technological struggle was universal across all major navies. In the Imperial Japanese Navy, the early fire control system, adopted in 1932, was a monument to this complexity. It required a crew of 11 personnel, crammed together in the director top. The range-taker struggled mightily to maintain lock on the same target as the director. The rangefinder itself lacked leveling, meaning its measurements were always unreliable when the ship was lively. Operators fought a system designed for precision, but crippled by the disunity of its own components. The Royal Navy faced its own iterative nightmare with the high-angle control system known as HACS. This was a continuous process of patching and upgrading a deeply flawed foundation. By the early 1920s, experts concluded that manual estimation was hopelessly error-prone. They needed an analog computer, the high-angle calculating table. HACS Mark I, which entered service in 1928, was an improvement, but it was deeply distrusted by those who understood the principle of garbage in, garbage out. Operators often had to manually smooth data, correct obvious errors, or even use entirely false setups just to bring the bursts into line with the target. They watched their shell bursts through angled eyepieces, frustrated because the pattern often told them the target was nowhere near where the computer said it should be. The introduction of the gyro rate unit in 1940 was meant to be a breakthrough, directly measuring angular rates to improve accuracy. But at long ranges and low sight angles, the manual warned, the rates could be grossly misleading. HACS was initially designed for aircraft flying at 130 knots. It was constantly pushed past its limit, struggling to handle climbing or diving targets. The British were forced to rely heavily on the octuple 2-pounder pom-pom, a weapon whose low muzzle velocity was already a technological anachronism against 1930s aircraft. Its director was of little use against dive bombers, forcing control officers to rely on eye shooting, literally aiming off based on instinct and tracers. The constant struggle to reload the unshielded, power-dependent mount under pressure, the constant risk of jamming due to weak cartridge cases, and the difficulty of maintaining accurate aim in a rolling ship defined the mundane physical struggle of the British anti-aircraft gunner. In contrast, the US Navy, benefiting from a later start, pushed for integration. The development of the Mark 37 system, begun in 1936, became the primary American medium-range fire control solution. It embodied the crucial realization that the computer needed to be protected below decks, while the director above needed to be a fully enclosed, integrated unit. The American adoption of superior stereo rangefinders also offered a significant advantage over the British coincidence rangefinders, but integration did not mean immediate perfection. The Mark 37 was a large, heavy system that created massive engineering challenges for naval designers trying to fit it into existing ship designs. More critically, initial installations proved disastrous due to instability problems. Many American vessels sailed to war with empty spaces where their Mark 37 directors should have been. Even once fixed, the Mark 37 was not a panacea. Personnel inside the director were badly cramped, and the separation of the pointer and trainer roles made coordination difficult. On a lively destroyer, the motion exacerbated the system's inherent instability. Facing lagging deliveries of the complex systems, the Bureau of Ordnance was forced to take what it called a desperate step. The solution was the ultra-simple Mark 51 director. This one-man unit, operating with a joystick, was a pragmatic retreat from complexity. It lacked the sophisticated predictive power of the Mark 37, but its simplicity and reliability made it shockingly effective, especially when paired with the Bofors 40mm gun. The race to aim was a constant battle of compromise. The British relied on patching legacy systems and using massive umbrella barrages from secondary armament to compensate for poor fire control accuracy. The Americans, though embracing superior integrated concepts, were constantly hampered by production bottlenecks and the sheer engineering challenge of fitting these systems into a warship. The fundamental instability of the ship and the impossibility of perfectly predicting a pilot's jinking maneuvers meant that the gunner's struggle remained a visceral, human fight against geometry, time, and the relentless motion of the sea. When the global conflict erupted in 1939, the crippling financial constraints and naval treaties of the interwar period vanished. They were replaced by a terrifying, immediate need for survival. The war in Europe acted as a brutal crucible, instantly exposing massive, fatal deficiencies in naval defense planning. The early campaigns off Norway and the devastating losses suffered by the Royal Navy off Crete provided the American Navy with a stark, undeniable warning. The lethality of shore-based air power was far beyond anything the Navy was prepared to resist. This strategic anxiety culminated in a single devastating demonstration of vulnerability in the Mediterranean. On January 8, 1941, the British fleet carrier HMS Illustrious, one of the jewels of the Royal Navy, was moving south of Malta. She was swarmed by German dive bombers. The attack was a symphony of destructive precision. The high-pitched shriek of the junker's Ju-87 Stuka sirens descended from 12,000 feet. That sound cut through the roar of the carrier's engines and the frantic barking of the pom-pom guns. The Illustrious was designed with an armoured hangar deck, a calculated risk intended to prioritize protection over aircraft capacity. But the German pilots delivered 1,000-pound armor-piercing bombs with the near-vertical accuracy of the Stuka. A plume of black smoke erupted violently from the flight deck as the first bomb penetrated the armored steel, exploding in the hangar bay below. The resulting thud was not the dull, distant concussion of a near miss, but a bone-jarring, intimate shockwave that rattled the teeth of every man on the bridge. The smell of cordite and burning oil instantly replaced the clean scent of the sea. Wave after wave of Stukas pressed the assault, their pilots focusing relentlessly on the now wounded capital ship. The British anti-aircraft defences, relying on the patched-up high-angle control system and the relatively low-velocity octuple pom-poms, were overwhelmed. The gunners struggled to keep pace, their manual adjustments hampered by the ship's evasive manoeuvres, their shots arriving seconds behind the target. The barrage fire, a desperation tactic formalized only a few years prior, turned the sky into a confusing mesh of inaccurate shell bursts. 6 massive hits ripped through the Illustrious. Below decks, the damage was catastrophic. The fleet commander, observing the attack, later remarked that the sight was fascinating, a word that captured the sheer, bewildered shock of watching a modern warship rendered helpless by coordinated air assault. The event proved that even the most heavily armored vessel could not withstand massed dive bombing. The era of the dominant, impervious battleship and the armored carrier was over. This lesson was quickly affirmed by the US Navy's own experience in the Pacific. While the illustrious attack exposed vulnerability, the Battle of Midway validated the offensive mastery of air power. The US Navy's SBD Dauntless dive bombers, flying from high altitude, achieved a hit rate vastly superior to level bombers. They were capable of delivering a 40% strike rate against maneuvering targets, compared to the mere 2% hit rate achieved by level bombers. Dive bombing was clearly the superior method for ship killing. The Japanese B-5N Kate torpedo bomber, highly effective in 1941, confirmed the lethality of coordinated multi-axis attacks that overwhelmed a ship's ability to maneuver. The strategic pendulum had swung violently. The single, heavy anti-aircraft shell, even with its explosive power, was too slow, too inaccurate, and too reliant on complex mechanical prediction systems that simply could not keep up with the speed and jinking of modern aircraft.
The only viable countermeasure was not precision but volume.
The US Navy, now unconstrained by treaties, plunged into a frantic, massive armament program. The quadruple 1.1-inch gun, the flawed stopgap, was immediately rendered obsolete by the arrival of the far superior Bofors 40mm and Oerlikon 20mm automatic weapons. The illustrious attack had shown that the crucial window for defense was the 1,500-yard final approach. This was a range where only rapid-fire automatic weapons could generate the dense wall of steel necessary to disrupt the attacker's aim or destroy the aircraft outright. The US Navy's designs, already reverting to larger hulls after the treaty expiration, could absorb the weight and space required for this armament proliferation. The destroyer leader Phelps, which had received one of the first 1.1-inch mounts, was soon eclipsed. Ships were quickly festooned with these new guns. The 40mm Bofors, with its high rate of fire and effective tracer rounds, became the new star of point defense. The logistical challenge was immense, but the iron law of mobilization dictated that they produce what was on hand, and quickly. The US commitment to this light anti-aircraft rush, symbolized by the sheer number of Bofors and Oerlikons that would eventually arm every major warship, was a direct, desperate response to the terrifying truth laid bare in the Mediterranean. If the fleet could not shoot down the enemy, it had to shake them, blind them, and overwhelm them with a hurricane of steel to survive the inevitable charge of the dive bomber. The fundamental shift in naval warfare was not marked by the sound of a gun, but by the silent sweep of a radar beam. The widespread adoption of systems like the US Navy's Mark IV and the later Mark 12/22, often paired with the Mark 37 Director, provided the fleet with eyes that saw beyond the horizon and through the blackest night. This was the technological advantage that compensated for the inherent limitations of analog fire control, finally enabling accurate, blind firing. In the Royal Navy, this technological leap necessitated a profound organizational change. The Air Defense Officer role, originating in the late 1930s, crystallized into the Gun Direction Room, part of the Action Information Organization. This was the nerve center where the flickering green PPI screens of the Type 79 air warning sets and the later Type 285 ranging radars. This new center maintained a continuous, crucial picture of the air situation around a ship. No longer did individual control officers rely solely on the limited view from their director tops. Now a single officer below decks could coordinate the entire defense, directing fighters and allocating fire zones based on electronic data. Yet as the Allied navies began to master the skies, the enemy introduced a threat that rendered the entire anti-aircraft gunnery paradigm instantly obsolete. It happened in the chaotic aftermath of the Salerno landings in September of 1943. The heavy cruiser USS Savannah was operating close to the Italian coast when the attack began. There was no dive bomber shriek, no low-level approach. There was only the high, distant drone of a German Dornier Do-217, far outside the 10,000-yard threshold, where the 5-inch 38 guns were designed to open fire. Suddenly, a small point of light appeared against the blue sky, detaching itself from the bomber. This was the FX-1400, the armor-piercing guided bomb, gliding silently on its preset course. It was a deadly, invisible threat, attacking from a standoff distance, unreachable by any conventional anti-aircraft battery. The crew of the Savannah opened fire in desperation. The 5-inch 38 spat shells that burst harmlessly thousands of yards short of the launching aircraft. The gunners and spotters, trained to track a maneuvering plane, were bewildered by the sight of the small winged projectile, guided remotely by radio command. They could see the flare in the tail, the small pyrotechnic trace that allowed the pilot 8 miles away to steer it. The FX-1400 plunged toward the Savannah's centerline. The anti-aircraft fire was a futile, furious display. The missile struck the roof of the No. 3 6-inch turret, penetrating the armor and detonating the powder charges waiting in the working chamber below. The resulting explosion was internal and catastrophic, blowing the turret roof straight up and sending a column of fire and shrapnel through the decks. 14 feet of the ship's bottom was ripped open. The sudden, immense shock of the hit, followed by the acrid smell of burning propellant, confirmed the new reality. Naval warfare was no longer a fight against piloted aircraft, but against guided machines that could not be deterred by shellfire. The FX-1490 and its rocket-boosted sister, the HS-293 glide missile, which sank the sloop HMS Egret and badly damaged other ships, forced a radical doctrinal shift. Evasive action, smokescreens, and most critically, electronic jamming became the primary defenses. The war had moved into the electromagnetic spectrum. The definitive countermeasure to this new era of aerial lethality was not a better gun or a faster computer, but a miniature radar housed in the nose of the shell itself. This was the VT proximity fuse, a technological marvel developed in secret. For years, the core gunnery problem had been defined by the dead time. This was the critical interval between the fire control operator manually turning a handle to set the fuse and the shell's eventual burst. If the fuse was set manually, the projectile might pass harmlessly ahead or behind the target, even if the trajectory was otherwise perfect. The VT fuse eliminated this geometrical problem by simply removing the need for a timed fuse altogether. When a shell carrying this new technology was fired, the tiny transceiver in its nose emitted a continuous radio wave. As the shell approached the target, the reflected signal grew stronger, and the resulting frequency shift, the Doppler effect, triggered the fuse to detonate automatically. The explosion occurred the moment the target was within the lethal radius, a mere 37 feet for a standard 4-inch shell. The effect was instantaneous and absolutely revolutionary. The Bureau of Ordnance admitted the VT fuse was the shot in the arm that allowed the existing, often inadequate fire control systems to stagger through the war. Suddenly, the 5-inch guns, which had struggled desperately against earlier drones, found their lethality multiplied exponentially. Against the kamikazes later in the war, the proximity fuse was responsible for 56% of kills achieved by 5-inch guns. This massive increase simplified prediction and gave the gunners a vital psychological edge. They no longer watched patterns of bursting shells, frustrated that the target was not where the computer said it should be. The sky simply erupted with shrapnel exactly where the enemy aircraft was flying. This technological leap was not confined to the defensive side. The Japanese, despite lagging severely in industrial capacity for electronics, were quick to adapt to this new electronic battlefield. When the US fleet descended upon Saipan, Japanese aircrews employed window. These bundles of aluminum strips, known universally as chaff, were designed to flood the American radar screens with false echoes. This move demonstrated a sophisticated understanding of electronic warfare. The continuous, invisible arms race was fully underway. Every technological leap in defense was met by a countermeasure, forcing the cycle of innovation to accelerate relentlessly. Naval warfare had transformed from a test of metal and powder to a battle fought with radio waves and analog foresight. By late 1944, the calculus of Japanese air warfare had been reduced to a single, desperate equation. They needed to achieve the maximum possible damage with the least amount of remaining resource. The veteran air groups that had fought in the first year of the war were gone, decimated by attrition and the disaster of the Battle of the Philippine Sea. Conventional attacks against the massive U.S. fleet were now a statistical impossibility. American ships were protected by integrated radar, centralized command in the gun direction rooms, and a hurricane of automatic fire. The U.S. Navy's superior anti-aircraft defenses forced the Japanese to abandon caution completely. If few aircraft returned home no matter the tactics, then the best strategy was one that promised to achieve something for the inevitable sacrifice. The strategic shift was finalized in the run-up to the invasion of the Philippines, culminating in the adoption of kamikaze, the human-guided missile. This was not mere fanaticism, but a brutal technological adaptation. The pilot himself became the ultimate, unjammable guidance system. The ultimate proving ground for this new tactic was the vast, terrifying expanse of the radar picket line off Okinawa in the spring of 1945. Destroyers were positioned 75 miles from the main fleet, their tripod radar masts carrying critical detection gear. Their duty was pure, sustained tension, the boredom and the fear of waiting for an attack, knowing they were the first, most exposed target. The alarm came without warning. General quarters screamed across the destroyer, Manat al-Abele. The air situation, relayed from the Action Information Organization, was chaotic. A massed wave of attackers, a mix of conventional bombers and something new, something terrifyingly fast. The first contact was a converted Zeke fighter carrying a heavy bomb, approaching in a low-level run before climbing for a steep dive. The 5-inch/38 battery, controlled by the Mark 37 system, opened fire instantly. The thunderous reports rocked the ship. The Mark 37 was now working in concert with the most powerful defense technology of the war, the VT proximity fuse. The sky ahead erupted in furious, expanding spheres of shrapnel, simplifying prediction by removing the human error of fuse timing. The barrage was effective. The Zeke shuddered, trailing smoke, but its pilot was committed. It plunged through the fire, and the explosion of its 500-kilogram bomb struck the ship's side. The concussion was violent, tearing through the hull. Fire erupted, and vital systems, including the main power feed to the anti-aircraft battery, flickered. This momentary failure threatened to render the guns almost useless, a grim echo of the Prince of Wales disaster earlier in the war. Before the crew could fully assess the damage, the second threat appeared. It was not an aircraft, but a blur, as this was the MXY-7 Oka, or Bucker, a specialized, rocket-propelled suicide missile. Unjammable and manned by a pilot strapped into its wooden airframe, it was approaching at a blistering speed, well over 500 knots. This velocity pressed the limits of the Mark 37's predictive capabilities. Range 4,000, too fast. The warning was redundant. The Mark 37's computer, designed to handle 400 knots, was lagging, its accuracy diminishing significantly as the target closed below 300 yards.
The defense devolved into a last, desperate act of local control.
The 40mm Bofors guns, the acknowledged star of the anti-kamikaze effort, swung violently, spitting tracer rounds in a thick, glowing stream. The gunners, operating the simple Mark 51 directors, held their joysticks steady, trying to walk the tracers into the incoming shape. The air was thick with the flash and bang of anti-aircraft fire, the acrid smell of cordite stinging the nostrils. The gunners watched the incoming shape, knowing the pilot would not jink, would not evade. This was the ultimate challenge to their skill, a target driven by human will and unyielding velocity. The Oka was too low, too fast. It struck the Manat al-Abele amidships, the impact a catastrophic final blow. The explosion was immediate, internal, and overwhelming. The destroyer broke into two pieces, sinking almost instantly. The sinking was a horrifying testament to the new reality. Despite the technological leap provided by the VT fuse and the tremendous volume of fire from the Bofors, which killed nearly 80% of kamikazes destroyed by automatic weapons, the sheer speed and single-mindedness of the suicidal attack could still prevail. The psychological toll on the survivors of the picket line was immense. They faced a warfare where the enemy's final tactical move was to turn his body into the weapon. This forced the gunner to not just break the plane, but to destroy the pilot's will mere feet from the hull. The U.S. Navy had mastered the geometry of prediction. Now it was fighting a war against desperation itself. The end of the war did not bring quiet to the shipyards. It merely redirected the relentless arms race from the battlefield to the drawing board. The staggering human and material cost of the aerial campaigns, culminating in the kamikaze blitz off Okinawa, cemented a single harrowing truth. The era of the conventional anti-aircraft gun, no matter how automated or voluminous its fire, was over. Naval air defense had begun the war as a collection of manually aimed pieces, but it had ended it as a complex integrated system of radar, analog computers, and proximity-fused ammunition. Yet the final, desperate attacks by the Oka and the calculated precision of the German guided missiles demonstrated that even this sophisticated system was brittle. It could still be overwhelmed by speed, by saturation, or by standoff distance. Post-war analysis quickly quantified the brutal reality of the anti-aircraft struggle. While direct kills by naval guns remained statistically rare, often less than 5% of all aircraft shot down, their crucial role lay in disruption. The sheer volume of fire from the Bofors and the shock of a VT-fused 5-inch shell burst forced pilots to jink violently, ruining their final approach and saving countless ships. The US Navy concluded that the pragmatic, mass-produced 40mm Bofors was the most effective short-range weapon, but its success was contingent on the organizational structure built around it. The centralized radar picture, the distributed fire control of the Mark 51, and the power of the proximity fuse. The true legacy of the war was thus the architecture of fire control. The Mark 37 Director, despite its initial instability and cramped internal space, became the conceptual foundation for future naval combat systems. Its below-decks computer, integrated with sophisticated radar like the Mark 12 and Mark 22, proved that the fire control problem was solvable only by separating the tracking optics from the complex calculations. This used electronics to overcome the limitations of human sight and mechanical prediction. The reliable 5-inch 38-caliber dual-purpose gun remained the standard medium-caliber weapon, but its limitations against the jet age were already apparent. The German FX 1400 and HS 293, attacking from outside the effective range of the 5-inch gun, proved that the next war would be fought not at 10,000 yards, but at 20,000 yards or more. The kamikaze, meanwhile, validated the concept of the supersonic unjammable terminal attack. This realization immediately accelerated the development of surface-to-air guided missiles, known as SAMs. Why bother calculating the future position of a maneuvering target and firing an unguided projectile? The projectile itself could now carry a radar receiver and continuously correct its own flight path. The US Navy's own BAT missile, the first successful radar-guided anti-ship weapon, had entered service in 1945, proving the concept of electronic guidance was sound. The logical successor to the Mark 37 system was not a better analog computer. It was the revolutionary Talos, Terrier and Tartar missile systems. The fire control team that had wrestled with the limitations of the Mark 37 Director, the layer, the trainer, and the range setter were replaced by a handful of technicians. They monitored radar consoles in the protected, quiet heart of the ship. The concept of channels of fire, driven by the need to engage multiple simultaneous attacks, evolved into the ability of a single missile launcher to coordinate the interception of dozens of threats. The constant roll and pitch that had entangled the two key angles of elevation and bearing for the World War II gunner were now irrelevant. The new weapons flew high above the trunnion tilt, guided by stable digital calculations. The desperate, visceral fight of the gunner, leaning back into his straps, squatting to load fixed rounds, hoping the proximity fuse would trigger in time, was finally over. The mundane struggle of bad coffee, lack of sleep, and the ubiquitous texture of mud. The effectiveness of naval anti-aircraft defense had been irrevocably defined as a complex, integrated system. The Mark 37, the 5-inch 38, and the Bofors were not obsolete. They were the evolutionary steps that led directly to the guided missile cruiser. The naval architect no longer designed a ship around the weight of a gun mounting and 200 rounds of ammunition. They designed it around the volume of a massive radar dome and the digital processing power required to launch and guide a supersonic interceptor. The victory in World War II had been secured by a hurricane of steel, but the future of naval defense belonged to the quiet, invisible power of the radar wave. If you value these historical accounts, please subscribe to the channel and like this video. It helps us preserve these stories. And please, Share your own memories or thoughts in the comments below.